In section 12.1, we learned about vector valued functions and how to work with them. In section 12.2, we're going to talk about how to compute calculus on these vector valued functions. So we're going to start with limits, work our way to derivatives, and then we'll also discuss integration on these vector valued functions. So to begin, let's talk about limits. They behave very similar to limits of real valued functions. So throughout this section, we're going to consider r of t to be a vector valued function. And we're going to assume that r of t is defined on an open interval that contains a, but possibly not at a. We're going to write the limit as t approaches a of r of t to equal L if and only if the limit as t approaches a of the magnitude of the vectors r of t minus L approaches 0. Now, this is the formal definition for the limit, but the very next theorem that follows basically says that limits of vector valued functions behave as you hope they would. In particular, if you're taking the limit of a vector valued function, then all you need do is take the limit of each of the component functions, making sure to maintain that vector setup. So you'll see that I notated them both with the angle brackets here and also with the IJK notation. Either of those would work just fine. So let's jump into our first example. We want to find the limit. Again, in each case, you can think of it as applying the limit to the first component and the second component. And then we're going to write out our answer as a vector. So we're taking the limit as t approaches infinity. As we look at this first component function, you have a couple of options here. Way back when in Calc 1, when we took limits to infinity, our first approach was to look at the highest power of t in the denominator and divide the numerator and the denominator by that power of t. So in this case, divide the top and bottom by t squared. Then we learned about L'Hopital's rule, which says if you're of the form 0 over 0 or infinity over infinity, which we are in this case, you can take the derivative of the top and bottom. So if you apply L'Hopital's rule twice, you will achieve an answer. But perhaps the quickest way is to just recognize that we have equal highest powers on top and bottom, namely t squared. So we can just take the ratio of those coefficients. Whoops. So that looks like an understood 1 over 3. So I'm perfectly fine with my students just writing 1 over 3 with the understanding that we've been working with limits to infinity for 2.5 semesters now, and we all know how to do that. So now what we want to do is we want to find the limit of the second component function. So now we're taking the limit as t goes to infinity of 1 over t, and of course we recognize that to go to 0. So again, absolutely no work is required for this problem. I am assuming that everybody has a sound understanding of limits here, so you can just write out your final answer. Limits brings us to continuity, and so we say that a vector valued function r is continuous at a point a if the two-sided limit as t approaches a of r of t equals r of a. This is the exact same definition that we use in Calc 1. We want to make sure that r is defined at a, that the two-sided limit exists, and that that two-sided limit is equal to the function value. So that's exactly what we're looking at here. And then we just note that we're continuous on an interval if we're continuous at each point. Now, we are also going to use all of our shortcuts that we learned in Calc 1. That is, you can assume polynomials are continuous, sine and cosine are continuous, the natural log function is continuous on its domain. Rational functions are continuous everywhere where they're defined. So all of those things are going to hold. You only need to use this definition when you can't use some of those other previous theorems that we learned in Calculus 1 or 2. So let's take a look at 5. We want to determine whether the function is continuous at 0. So we're only checking at t equals 0 and then explain your reasoning. So let's take a look at part A. We have two types of functions here. So we know that the function sine of t is continuous everywhere, and negative 2t is a polynomial, so it's also continuous everywhere. So in particular, it's also true that these are continuous at t equals 0. All right. So again, I'm not even going through that formal definition up above, just using my knowledge of sine and cosine and polynomials and stating that. So for explain your reason, you can either go through computing the limit or you can just explain in words as I just did. Let's take a look at B. All right, t squared and t, those are both polynomials. So we have no issues there. If we take a look at 1 over t, we have a problem, right? Because we're checking continuity at 0, and so 1 over t is not defined at t equals 0. This is a problem, so that merits a sad face, right? If we're not defined, then we have no hope of continuity. And so the answer is no, we're not continuous at 0 for the reason that I just stated, that 1 over t, the middle component function, is not defined at 0. All right, so moving on from limits and continuity, we want to talk about differentiability. So again, assuming r of t is a vector valued function, the derivative of r with respect to t is given by the limit as h approaches 0 of the difference quotient. So r of t plus h minus r of t divided by h. All right, the domain of the derivative is all the t values for which that limit holds up above. And we say that the function is differentiable at t if the limit exists. Now, this is the formal definition. You might recognize this from Calc 1 when we first defined the derivative. That being said, again, I am assuming that everybody has a strong background in differentiation, and we will never use this formal definition. Okay, so before we get to that, let's talk about different ways to denote the derivative of a vector valued function. If the variable is understood, then we'll use the prime notation, right? Which means there's only one variable to take the derivative with respect to, so that prime notation is fine. To really emphasize what we're taking the derivative with respect to, this Leibniz notation is preferred. All right, due to the mathematician Leibniz. It can also be expressed in this way if you really want to emphasize the fact that r is dependent on t. So I'll use all 4 of these notations interchangeably. Just wanted you to recognize that. All right, so how does the derivative relate to the graph of the function, right? What is the geometric interpretation? So here we're going to suppose that C is the graph of your function r, and that could be in 2 dimensions or 3 dimensions. This holds in either dimension. And then let's suppose that the derivative r prime of t exists and is non-zero. Okay, so if that's the case, if we position the derivative vector r prime of t with its initial point at the terminal point of the vector r of t, so that is where r of t ends, we want r prime of t to begin. Then geometrically, what's going to happen is this derivative vector r prime of t is going to be tangent to the curve, and furthermore, it points in the correct orientation. So these are 2 important things to keep in mind geometrically what's happening. So if you think of a physics class and you learned about circular motion, you learn that if you are, for example, swinging a ball on the end of a rope in circular motion and all of a sudden you let go, that ball is going to swing off tangential to the circular motion. All right, same thing here, that derivative is always going to be tangent to the curve at the point that you're calculating your derivative at. So theorem 5 tells us, look, that's great and all that we can compute the formal limit as h approaches 0 of the difference quotient, but we can save ourselves some time. We're pros at computing derivatives of single variable functions. And so it says, if you want to take the derivative of a vector valued function, you need only take the derivative of each component functions. Do note that the derivative of a vector valued function is a vector. So still make sure that you write it either with the IJK notation or with the angle bracket notation to emphasize that this is a vector. All right, so let's take a look at an example here. We want to sketch the circle that's defined by cosine t I hat plus sine t j hat. And then what we want to do is we want to sketch the vector in parts A and C on that circle to see the geometric interpretation here. So let's start by sketching this circle. All right, so let's do our XY axes. And we recognize this to be a circle, in particular the unit circle where X is cosine T and Y is sine T. And be sure to indicate the orientation of this vector valued function. So we know that the unit circle is oriented counterclockwise. All right, so first we want to compute the derivative vector and then evaluate it at pi over 4 and then sketch it on the circle. So let's start by finding the derivative of r. The derivative of cosine is negative sine. The derivative of sine is cosine. And now we would like to evaluate it at pi over 4. So this is negative root 2 over 2, positive root 2 over 2. All right, and so what we want to do is we want to plot this vector where its initial point is starting at the terminal point of r of pi over 4. So here's r of pi over 4. Let me actually do it in a different color. This is r of pi over 4. All right, and then let's do in purple the derivative. So we want to begin the derivative vector at the terminal point of r of 4. So you can see that dot that I just made in purple. We want to go negative 2 root 2 in the x direction and positive 2 root 2 in the y direction. All right, and so what that's going to look like is it's going to be coming off at kind of a 45 here in this direction. So this purple vector is r prime of pi over 4. All right, and so you can see that tangential nature of r prime as it comes off of the r of pi over 4 vector. All right, the next example is not with the derivative vector, but with the difference. So what I'm going to do here is I'm going to start by evaluating r of t at 2 pi. So what is cosine of 2 pi? That's 1. And sine of 2 pi is 0. And then I want to subtract off r of 3 pi halves. So cosine of 3 pi halves is 0. Sine of 3 pi halves is negative 1. So when I subtract these vectors, I get a 1, and double negative makes a positive 1. All right, so how do I accurately sketch this on the picture that we have drawn? So if you'll remember, if we had points P and Q, and we wanted to find vector PQ, remember what we did? We took the points in Q and subtracted off the points from P, right? It's always the terminal minus the initial. That's exactly how you can interpret this. So r of 2 pi would be considered the terminal point. R of 3 pi halves would be considered the initial point. And so I'll change my color to red. If we start at the initial point, 3 pi halves, we want to go up 1 and then over 1. And sure enough, we're ending precisely at 2 pi. So this vector, r of 2 pi minus r of 3 pi halves, is the vector whose initial point is at 3 pi halves on the unit circle and ends at 2 pi on the unit circle. And it has a length there of the square root of 2. So just forming that isosceles triangle there in red. All right. So next, we'd like to introduce some rules for differentiation. Most of these are not going to be surprising. So vector valued functions behave nicely under differentiation. Just note here what we're starting with. R of t, R1 of t, and R2 of t are going to be differentiable vector valued functions. F of t is a real valued function. All right, so that's important to note. That's not a vector valued function, which is why it's not in bold. And then we have a scalar c and a constant, or a scalar k and a constant vector c. Again, that c is bold because it's representing a vector. All right, so number 1 says that the derivative of a constant vector is 0. Very similar to the derivative of a constant number is 0, right? Number two, if you have a scalar times a vector valued function, you can always pull that scalar out front and then just take the derivative of the vector valued function. Numbers 3 and 4 just say that the derivative of a sum is the sum of the derivatives, and similar for differences. So in other words, the derivative operator can be distributed, across sums and differences. Number 5 is really the only new or interesting property here that we haven't necessarily seen before. Notice what we're doing. We're computing the derivative of a real valued function times a vector valued function. And what happens is this derivative obeys the product rule. So the standard product rule from Calc 1. And what that says is you're going to leave your real valued function f of t, multiply it by the derivative of r of t, plus the derivative of your real valued function f of t times that vector valued function r of t. So again, the product of a real valued function times a vector valued function obeys the product rule. All right, so next we want to find the derivative r prime evaluated at a particular t naught value, and then we also want to sketch the graph of our function together with its derivative. So this is just again going to geometrically show that relationship between the original graph of the function and the derivative. So let's start by finding the general derivative function for all t. Based on a theorem that we had earlier, we can just take the derivative of each component function. So that gives us 1 and 2t. Next, let's evaluate that derivative at the specified t naught value, in this case 2. So I'm getting out 1 and 4. So now what I'd like to do is I would like to sketch this graph of the function r of t together with the derivative. There's a way for me to do a sticky, but I can't remember how to do it. So we will just sketch it freehand. So here's x and y. And let's start by sketching the original graph. I'm just going to do for t greater than or equal to 0, but certainly you could also do for negative t values. So if I plug in 0 for t, I get 0 out for x and y, so 0, 0. Next, let's plug in 1 for t. I get out 1 for x and 1 for y. When I plug in 2 for t, I get out 2 for x and 4 for y. And I'm trying to graph this as accurately as possible. Let's do one more. Let's do 3. If I plug in 3 for t, I get out 3 for x and 9 for y. So 5, 6, 7, 8, 9. All right. So now what I'm going to do is I'm going to sketch in this half of the parabola. I'm going to note the orientation. Okay, and so again, it would be the same on the other side. I just haven't sketched those negative t values. And now what we want to do is we want to sketch this derivative vector right here. Now remember, we would like to sketch it so that its initial point is at the terminal point of r of 2. So here was t equals 2, was at this point right here. So I'm going to begin my derivative vector on that purple dot, and then I'm going to move over 1, and I'm going to move up 4. So 1, 2, 3, 4. It's really close to my curve because it's just ever so slightly curving there. But this purple vector is r prime of 2. And again, you can visually see based on our graphing skills that this vector is tangent to that parabolic curve. All right, so moving forward here, we have one more definition talking about tangent vectors and tangent lines. So let P be a point on the graph of a vector valued function r of t, and let r of t naught be the radius vector from the origin to P. If that derivative vector exists and that vector is non-zero, then we call the derivative a tangent vector to the graph of r of t at r of t naught. All right, so right here we can see exactly why this is being called a tangent vector, because of that geometric relationship that derivatives are always tangent to the curve. And we call the line through P that is parallel to the tangent vector the tangent line of the graph. And so this equation right here should look familiar. It looks like the parametric equation of a line. So way back in section 11.5, we had learned about parametric equations of lines. In particular, we took the point and we added it to t times the vector. So we're going to use this equation of the tangent line then to find those tangent lines, just leaning back on our information from section 11.5. So let's take a look at 24. Find a vector equation of the line tangent to the graph of R at the specified point. All right, so we have our equation R of t. Let's begin by finding the derivative function R prime of t. So I'm going to write this in the angle bracket notation, but as always, you're welcome to use the I hat, j hat notation. Derivative of cosine is a negative sign. And the derivative of negative 3t is negative 3. All right, so we have our derivative. We would like to evaluate it at our specified t naught value. So something that's a little bit different in this problem is we don't have a t naught. Right? Instead, they actually gave us the point p naught at 2 comma negative pi. All right, so the question becomes, what t naught value corresponds to this p naught point? So t naught equals what, so that 4 cosine of t naught comma negative 3 t naught equals 2 and negative pi. So you have two equations with only one unknown. Pick your favorite equation to work with. I'll work with the y component functions. And so what I have is negative 3 t naught equals negative pi. And if I solve for t naught, I see that t naught equals pi over 3. So we had to do a little bit of extra work there just to identify what our t naught value is. But now that we have that, let's go ahead and evaluate our derivative vector valued function, at that t naught value, pi over 3, and that's going to give us our tangent vector. So we want negative 4 sine of pi over 3, comma, negative 3. All right, so sine of pi over 3 is a square root of 3 over 2. And then, of course, we have the constant negative 3. So we're getting negative 2 root 3, comma, negative 3. All right, so this is going to be our vector v naught. All right, this is our tangent vector. R naught is just R evaluated at t naught, which actually was that point that they gave us, 2 negative pi. So we now have all of the pieces and parts to come back up to this highlighted equation up above and pull it all together to find our equation of the tangent line. So our equation is the following. You can either write it in this angle bracket notation, 2 comma negative pi plus t times negative 2 root 3 comma negative 3, okay? Or you could write it in the ij notation. So I'm just gonna squeeze it in right down here. You could say r of t equals 2I hat minus pi j hat plus t times negative 2 root 3 I hat minus 3 j hat. All right, so whichever notation you prefer works just as well. I tend to use that angle bracket notation. All right, so we talked about how to find derivatives of sums of vector valued functions, differences of vector valued functions, and a product of a real value and a vector valued function. we didn't talk about products of two vector valued functions. And part of the reason is because when we talk about products of vectors, there are two different products. We have the dot product and we have the cross product. So you can't just talk about products in general, you need to specify which product you're talking about. And so this remark at the bottom of page 3 here is just telling you how the dot product and cross product behave under differentiation. And as it turns out, both of them follow the standard product rule, with the understanding that the product that's being used is either the dot product or the cross product. So for this first one, you're going to just repeat R1 and dot it with the derivative of R2, plus the derivative of R1 dotted with R2, and then the same thing down here below, but just repeating it with the cross product. So both the dot product and the cross product follow the standard product rule from Calc 1. All right, so we're going to end this section here with integration. Theorem 8 says that if you have a differentiable vector valued function in 2 or 3 dimensions, and if the magnitude is constant, then what we know is that R dotted with R prime equals 0. So when we think back to our knowledge of the dot product, what does it mean when two vectors dotted together equals 0? It means that they're perpendicular. So this is saying that if your magnitude is always constant, then your function and its derivative function are always orthogonal. So this is very specific to constant magnitudes, all right? That's one of the main hypotheses in Theorem 8. We have a further remark here that says if your vector valued function is continuous on an interval from A to B, then if you're taking the integral of a vector valued function, it's the same as just integrating each component function independently. And again, making sure to write your final answer as a vector. So that ijk is important. You can also use the angle bracket notation. So this remark is written in terms of 3-dimensional functions. A similar result holds in 2 dimensions. Finally, vector valued functions behave nicely under integration. Number 1 of Theorem 9 just says that constants can be factored out in front. And then numbers 2 and 3 says that the integration can distribute across sums and differences. So nothing surprising here. These vector valued functions behave as you think they would behave. So we'll end here with a couple of examples of integration. For 34, we want to calculate the integral. This one's easy enough that we don't even need any fancy techniques of integration. I won't even show any work here because I think we'll all feel comfortable. The integral of e to the negative t. If you wanted, you could do a quick u substitution with negative t, and you'll see that that's going to pop out a negative sign. So this is negative e to the negative t. The integral of e to the t is itself. And then the integral of 3t squared, you're just going to add 1 to that exponent, divide through, and you'll get t cubed. Now, this was an indefinite integral. So if you think back to Calc 1 and Calc 2, make sure you add your constant of integration. In this case, it's a constant in each term. So you can either tack on a plus C1, a plus C2, or a plus C3. But what I like to do is I like to just say plus some constant vector. And the components of that vector could differ in each component. So I just write it generally as a plus C. But you could, of course, add the plus C as a scalar in each of the components. 38 is a definite integral, so we don't need to worry about that plus C constant vector. However, this one we're going to need some u substitution. So I'm going to set up 2 individual u substitutions. The first one is going to be for the first component function. So I'm going to let u1 equal 3 minus t. And then I'll note that its derivative is going to be a negative dt. And then similarly, for the second component function, I'm going to let u be 3 plus t, and its derivative is dt. All right, so keeping that in mind, what I have now is the integral from negative 3 to 3 of u1 to the 3/2 power dt. And, excuse me, not dt. It's going to become du1. And this is in the I hat component. And actually, let's leave those limits of integration off, and we'll plug them back in after we have plugged back in for U1. And let's do a similar setup for the second integral. We swapped that 3 plus t out for a U2, so this becomes U2 to the 3/2 power du2. And this is in the j hat component. And of course, the last one I can integrate 1, that just becomes t, and this is evaluated from -3 to 3. I do not need a plus c on the end, but I will include my k hat. All right, so now let's carry out this integration. Remember, I want to add 1 to the exponent. That makes it 5/2, and then divide through by that 5/2. So that makes it a 2/5. I'm going to go ahead and just resubstitute for a 3 minus t. And then we want to evaluate from -3 to +3. And then same thing here in this second component function, only it's 3 plus t. And then that last, oh shoot, I forgot my j hat. That last term there is a 3 minus a -3 gives us 6 in the k hat component. All right, so now let's evaluate. So we have 2/5. So first I have a 0 raised to the 5/2 power minus a 6 raised to the 5/2 power. And that's in the I hat. Similarly, for the next one, when I plug in 3, I get 6 to the 5/2. When I plug in -3, I get out 0. And this is j hat, and we still have our 6 k hat. So after cleaning things up a bit, we note that we have 2/5 negative, 6 to the 5/2 power, and maybe I'll put parentheses around there to indicate the 5/2 only goes to the 6. Then I have plus 2/5, 6 to the 5/2 power in the j hat, 6 in the k hat. So this is my final answer for the definite integral in problem 38. All right, that's all for today's lecture. Join back here for section 12.3.